Swayam Prabha. Digital India. Educated India.
This lecture is on linear algebra for data science. Linear algebra is a very fundamental part of data science, and usually a typical one semester linear algebra course will run for about 36 hours. What we are trying to do here is we are trying to introduce the use of linear algebra in data science in a few hours. So that necessarily means that we cannot cover the topic of linear algebra in all its detail. However, what we have attempted to do here is to identify the most important concepts from linear algebra that are useful in the field of data science, and in particular for the material that we are going to teach in this course. So in that sense, we have crystallized a few important concepts from linear algebra that the participants should learn and understand. So that's one thing that I'd like to mention right at the beginning. The second thing that I would like to mention is the following. Linear algebra can be treated very theoretically, very formally. However, in this short module on linear algebra, which has relevance to data science, what we have done is we have tried to explain the ideas in as simple a fashion as possible without being too formal. However, we do not do any hand waving. We teach linear algebra in a simple fashion. So that's another thing that I would like you to remember as we go through this material. So we first start by explaining what linear algebra is useful for. So when one talks about data science, data representation becomes an important aspect of data science, and data is represented usually in a matrix form, and we are going to talk about this representation and concepts in matrices. The second important thing that one is interested from a data science perspective is, if this data contains several variables of interest, I would like to know how many of these variables are really important, and if there are relationships between these variables, and if there are these relationships, how does one uncover these relationships? So that's also another interesting and important question that we need to answer from the viewpoint of understanding data. Linear algebraic tools allow us to understand this, and that's something that we'll teach in this course. And the third block that we have basically says that the ideas from linear algebra become very, very important in all kinds of machine learning algorithms. So one needs to have a good understanding of some of these concepts before you can go and understand more complicated or more complex machine learning algorithms. So in that sense also, linear algebra is an important component of data science. So we will start with matrices. Many of you would have seen matrices before. I'm going to look at matrices and summarize the most important ideas that are relevant from a data science viewpoint. What is a matrix? A matrix is a form of organizing data into rows and columns. Now there are many ways in which you can organize data. Matrix provides you a convenient way of organizing this data. So if you are an engineer and you are looking at data for multiple variables at multiple times, how do you put this data together in a format that can be used later is what a matrix is helpful for. Now matrices can be used to represent the data, or in some cases matrices can also be used to represent equations, and the matrix could have the coefficients in several equations as its component. Now once we generate these matrices, then you could use the linear algebra tools to understand and manipulate these matrices. so that you are able to derive useful information and useful knowledge from this data. So let's start and then try and understand how we can understand and study matrices. As I mentioned before, matrices are usually used to store and represent data on machines, and matrix is a very natural approach for organizing data. Typically, when we have a matrix, it is a rectangular structure with rows and columns. In general, we use the rows to represent samples, and I'll explain what I mean by this in subsequent slides, and we use columns to represent the variables or attributes in the data. Now, this is just one representation. It is possible that you might want to use rows to represent variables and columns to represent samples, and there's nothing wrong with that. However, in this course and all the material that we present in this course, we will stick to using rows to represent samples and columns to represent variables as far as this course is concerned. Let me explain matrix using a real life example. Let's consider that you are an engineer and you are looking at a reactor which has multiple attributes, and you are getting information from sensors such as pressure sensors, temperature sensors, and density, and so on. Now let's assume that you have taken 1000 samples of these variables. Now you want to organize this data somehow so that you can use it for purposes later. One way to do this is to organize this in this matrix form, where the first column is the column that corresponds to the values of pressure at different sample points. The second column corresponds to the value of temperature at several sample points, and the third column corresponds to the value of density at several sample points. So that's what I meant when I said the columns are used to represent the variable. So each column represents a variable. Column 1 pressure, column 2 temperature, and column 3 density. And when you look at the rows, the first row represents the first sample. Here in the first sample you will read that the value of pressure was 300, the value of temperature was 300, and the value of density was 1000. Similar to that, you will have many rows corresponding to each sample point up to the last row, 1000th row, which is a 1000th sample point, which says the pressure is 500, temperature is 1000, and density is 5000. Let's take another example. Let's say I have two vectors, x 1 2 3 transpose and y is 2 4 6. Let's say this is some variable that you have measured and y is some other variable you have measured, and the three values could represent the three sampling points at which you measured these. Now we have been talking about using matrices to represent data from engineering processes, sensors, and so on. The notion of matrix and manipulating matrices is very important for all kinds of applications. Here is another example where I am showing how a computer might store data about pictures. So for example, if you take this picture here on this left hand side and you want to represent this picture somehow in a computer, one way to do that would be to represent this picture as a matrix of numbers. So in this case, for example, if you take a small region here, you can break this small region into multiple pixels, and depending on whether a pixel is a white background or a black background, you can put in a number. So for example, here you see these numbers which are large numbers which represent white background, and you have these small numbers which represent black background. So this would be a snapshot or a very small part of this picture. Now when you make this picture into many such parts, you will have a much larger matrix, and that larger matrix will start representing the picture. Now you might ask, why would I do something like that? There are many applications where you want the computer to be able to look at different pictures and then see whether they are different or the same, or identify subcomponents in the picture and so on, and all of those are done through some form of matrix manipulation, and this is how you convert the picture into matrix. Now notice that while we converted this matrix, we have again got into a rectangular form where we have rows and columns where data is filled as a representation for this picture. So the image that I showed before could be stored in the machine as a large matrix of pixel values across the image, and you could show other pictures and then say, are these pictures similar to this, are they dissimilar, how similar or dissimilar, and so on. And the ideas from linear algebra and matrix operations are at the heart of these machine learning algorithms. So in summary, if you have a data matrix, I said the data matrix could be data from sensors in an engineering plant, it could be data which represents a picture, it could be data which is representing the model where you have the coefficients from several equations. So the matrix basically could have data from various different sources or various different viewpoints, and each data matrix is characterized by rows and columns, and the rows represent samples and the columns represents attributes or variables. Now that we have understood how we generate a matrix and why we generate matrices, the next question might be the following. Supposing I have a matrix where I have several samples and several variables, I might be interested in knowing if all the variables that are there in the data, are they important. In other words, I would really like to know of all these variables how many are actually independent variables, so that I know how much information is there in this data. So if let's say I have thousands of variables and of those there are only 4 or 5 that are independent, then it means that actually I can store values for only these few variables and calculate the remaining as a function of these variables. So it is important to know how much information I actually have. So this would lead to the following questions. The first question might be, are all the attributes or variables in the data matrix really relevant or important? Now a sub question is to say, are they related to each other? If I can write one variable as a combination of other variables, then basically I can drop that variable and retain the other variables and calculate this variable whenever I want. Okay, so that's a very important idea that we want to use in machine learning and various other applications. So how do I find out how many of these variables are really independent? And let's assume that I do find that only a few variables are really independent. Then how do I identify the relationship between these variables and the other dependent variables? And once I do that, how do I actually reduce the size of the data matrix and so on, are questions that one might be interested in answering. So let's consider the example that we talked about, the reactor with multiple attributes. In the previous slide we talked about pressure, temperature, density. Here I have also included viscosity. Let's say I have 500 samples. Then when I organize this data with the variables in the columns and samples in the row, then I will get a 500 by 4 matrix where each row represents one of the 500 samples, and if you go across the column, it will represent the variable values at all the samples that we have taken. Now I want to know how many of these are really independent attributes. So from domain knowledge, it might be possible to say that density is in general a function of pressure and temperature. So this implies that at least one attribute is dependent on the other, and if this relationship happens to be a linear relationship, then this variable can be calculated as a linear combination of the other variables. Now if all of this is true, then the physics of the problem has helped us identify the relationship in this data matrix. The real question that we are interested in asking is if the data itself can help us identify these relationships. Let's first assume that we have many more samples than attributes for now, and once we have the matrix, when we want to identify the number of independent variables, the concept that is useful is the rank of the matrix, and the rank of the matrix is defined as the number of linearly independent rows or columns that exist in the matrix. And once you identify these number of linearly independent rows or columns, then you could basically say that I have only so many independent variables and the remaining are dependent variables. So consider this example here, where I have this A matrix which is 1 2 3 2 4 6 1 0 0. If you notice, this matrix has been deliberately generated such that the second column is twice column 1. So in other words, the second column is dependent on the first column, or you could say the first column is dependent on the second column. Now there is one other column which is independent of these two. So if you think about this matrix, there are two independent columns, which basically means there are two independent variables. So the notion of rank is important. It allows us to work with a reduced set of variables, and once we identify the independent variables, the dependent variables or attributes can be calculated from the independent variables if the data is being generated from the same data generation process. And if you identify that there are certain variables which are dependent on other variables, and as long as the data generation process is the same, it does not matter how many samples that you generate, you can always find the dependent variables as a function of the independent variables. Now that we have talked about identifying how many independent variables are there, assume that the number of independent variables are less than the number of variables, then that basically automatically means that there are linear relationships between these variables. Now we ask the next question as to how do we identify these linear relationships among variables or attributes. So this question of how does one identify the linear relationships among the attributes is answered by the concepts of null space and nullity, which is what we are going to describe now. When we have a matrix A, and if we are able to find vectors beta such that A beta equal to 0 and beta not equal to 0, then we would call this vector beta as being the null space of the matrix. So let's do some simple numbers here. For example, if A is a 3 by 3 matrix, because beta multiplies A, beta has to be 3 by 1, and the resultant will be some 3 by 1 vector, and if all the elements of this 3 by 1 vector are 0, then we would call this beta as being in the null space of the matrix. Now interestingly, the size of the null space of the matrix provides us with the number of relationships that are among the variables. If you have a matrix which is of dimension 5, and let's say the size of null space is 2, then this basically means that there are two relationships among these 5 variables, which also automatically means that of these 5 variables only 3 are linearly independent, because the two relationships would let you calculate the dependent variables as a function of these independent variables. Now let's look at this in little more detail to understand how we can use this null space vectors. Let's assume that I have a matrix such as this. Now if there is a beta, which is what we have written here, such that A times beta equal to 0, as I mentioned in the previous slide, if I have this matrix of this dimension, and if I multiply beta with this matrix, then on the right hand side there are going to be several elements, and for beta to be the null space of this matrix, every one of the elements has to be equal to 0. Now let's look at what each of these elements are equal to. So if you take the first element on the right hand side, that would be a product of the first row of this data matrix and this beta vector, which would basically be x11 beta 1 plus x12 beta 2 all the way up to x1n beta n equals 0. Now similarly, if you get to the second row and multiply the second row by this vector, you will get another equation. So if you keep going down, for every sample, if you write this product, you are going to get an equation. The last sample, for example, will be xm1 beta 1 plus xm2 beta 2 plus xmn beta n equals 0. Now there is something interesting that you should notice here. This equation seems to be satisfied for all samples. So what this basically means is, irrespective of the sample, the variables seem to hold this equation, and since this equation is held for every sample, we would assume that this is a true relationship between all of these variables or attributes. So in other words, this beta 1 to beta m gives you in some sense a model equation or a relationship among these variables. So one might say that this equation can generally be written as x1 beta 1 plus x2 beta 2 all the way up to xn beta n is 0, where you can take any sample and substitute the values of the variables in that sample at x1 x2 up to xn, and this is to be satisfied. So this is a true relationship. So this is what we have said again here. Notice that if a beta equal to 0, every row of a when multiplied by beta goes to 0. So this implies that the variable values in each sample behave the same. So we have truly identified a linear relationship between these variables. Now every null space vector corresponds to one such relationship, and if you have more vectors in the null space, then you have more relationships that you can uncover. So we will demonstrate this example, this with a further example. So this rank nullity theorem basically says the nullity of matrix A plus the rank of matrix A is going to be equal to the total number of attributes of A or the number of columns of the matrix. So the nullity of A tells you how many equations are there. There are so many vectors in the null space. The rank of A tells you how many independent variables are there, and when you add these two, you should get the total number of variables that is there in your problem. So to summarize, when you have data, the available data can be expressed in the form of a data matrix, and as we saw in this lecture, this data matrix can be further used to do different types of operations. We also defined null space. Null space is defined as a collection of vectors that satisfy this relationship A times beta equal to 0. So this basically helps in identifying the linear relationships between the attributes or the variables directly, and the number of such vectors or number of such relationships is what is given by the nullity. Nullity of the matrix tells you how many relationships are there or how many vectors are there in the null space. Let us take some examples to make these ideas a little more concrete. Let us take a matrix A which is 1 3 5 2 4 6. A quick look at this matrix and the numbers would tell you that these two columns are linearly independent, and subsequently, because these columns are linearly independent, there can be no relationships among these two variables. So you can see that the number of columns 2, since they are independent, the rank is 2. Since the rank is 2, nullity is 0, right? Because both the variables are independent, you cannot find a relationship. If you were able to find a relationship, then the rank should not have been 2. So this basically implies that null space of the matrix A does not contain any vectors, and as we mentioned before, these variables are linearly independent. Now let us take the other example that we talked about, where I mentioned that we have deliberately made the second column twice the first column. So in this case, as we saw before, the rank of the matrix will be 2 because there are only 2 linearly independent columns, and since the number of variables is equal to 3, nullity will be 3 minus 2 equal to 1. So when we look at the null space vector, you will have one vector which will identify the relationship between these 3 variables. So to understand how to calculate the null space, let us look at this example. So we set up this equation A beta equal to 0, and we know we will get only one beta here, and beta we have written as b1 b2 b3, and when we do the first row versus column multiplication, I will get b1 plus 2 b2 equals 0. When I do the second row and column multiplication, I will get 2b1 plus 4b2 equal to 0, and when you do the third multiplication, you will get b3 equals 0. Now the second equation, which is 2b1 plus 4b2 equal to 0, is simply twice the first equation, so that does not give me any extra information, so I have dropped that equation. Now, when you want to solve this, notice that B3 is fixed to be 0. However, from this equation what you can get is B1 is minus 2B2. So, what we have done is, instead of B1 we have put minus 2B2, retained B2 and 0. This basically tells us that you can get a null space vector which is minus 2 1 0. However, whatever scalar multiple you use, it will still remain a null space vector. So, this is easily seen from the following. If A times beta equals 0, where beta is a vector, A is a matrix, let us assume I take some other vector from beta, which is some C beta, where C is a constant. Then if I plug it back in, I will get A times C beta equals 0, which, because this is a scalar, I can take it out, C A beta equals 0. Since this is 0, C times 0 will be 0. So, this will be also 0 vector. So, whenever beta is a null space vector, then any scalar multiple of that will also be a null space vector. That is what is seen by this K here. Nonetheless, we have a relationship between these variables, which is basically saying minus 2x1 plus x2 equals 0 is a relationship that we can get out of this null space vector. So, to summarize this lecture, as we saw, a matrix can be used to represent data in rows and columns, representing samples and variables respectively. Matrices can also be used to store coefficients in several equations, and which can be processed later for further use. The notion of rank gives you the notion of number of independent variables or samples. The notion of nullity identifies the number of linear relationships, if any, between these variables, and the null space vectors actually give us the linear relationships between these variables. I hope this lecture was understandable, and we will see you again in the next lecture. Thank you.